So this is the free energy and the chemical equilibrium. And let's see the relationship between standard free energy and free energy. So this is the equation for the free energy, Gibbs free energy, by using the standard free energy and the Q reaction quotient. For the given reaction, QP, reaction quotient equals pressure of the product in a gas state raised to the power of 2 over the pressure of the reactant in a gas state. We do not include solid substances as in a solid state or a liquid state. So, and if the pressure are given, then we can find that the QP for this reaction equals 2.25. So, knowing that the delta G standard for the given equation equals 2.60 kilojoules, and this is the R, the gas constant, in kilojoules over K mole. The temperature is 25 degrees Celsius, which is 298 Kelvin. And I will put the logarithm of the QP, and we'll say that the delta G for the reaction equals 4.3 kilojoules per the mole of the reaction. So, and we can calculate the delta G for the reaction, and we can actually predict the direction in which the reaction will proceed spontaneously to establish equilibrium. So take a look at the example 18.8 on your screen. And this is the dinitrogen tetraoxide decomposing into nitrogen dioxide. And Kp for the reaction is 0.113 at 298 Kelvin. And the standard free energy for this reaction is 5.4 kilojoules per mole. So let's say for the certain experiment, the initial pressure of the substances are provided to us. They want us to calculate the delta G for the reaction and predict which direction the reaction will reach to establish the equilibrium. So we're going to use this formula. We will find the QP, so that because they are giving us initial pressure, this is not the equilibrium pressure, this is initial pressure. So we'll take initial pressure of the NO2, which is 0.122 atm. We will raise it to the power of 2, and we divide this by the pressure of N2O4, which is 0.53, and we will find the QP over here. Then we will use this equation. We will standard free energy is given to us in a problem. R is universal gas constant with the kilojoules, temperature to 98 Kelvin, and this is a QP. And we will see that the delta G is equal to minus 3.1 kilojoules per mole. So, and as we know, if the delta G is negative, that means the reaction will proceed spontaneously in a forward direction or from left to right, because the delta G is negative, and that's what spontaneity means. It means the delta G has to be negative. So, what is the relationship between the delta G standard and the K? So, when the reaction will reach the equilibrium, that means delta G will equal to 0, and the Q becomes the K. It's the equilibrium constant. So because the reaction will reach the equilibrium. So we can rearrange this equation, because at equilibrium, delta G standard, delta G, I'm sorry, equals to 0, and the Q becomes K, it's equilibrium. So we can find that the standard free energy really equals to minus RT ln K. So, and this graph just shows to us relationship between the delta G being negative and the Kelvin, really the relationship. So This is the relationship between the K, and this table shows this a little better, the relationship between the Kelvin, the equilibrium constant K and the standard free energy. So if the K is greater than 1, um, if the K is greater than 1, so that means if I will take a logarithm of that K, I will get a positive number, and delta G standard becomes negative. At equilibrium, we really will have products favored. But even if I will look at the K is greater than 1, is mean that the ratio between the ratio of the numerator to the denominator is greater than 1. That means I have a more numerator than the denominator. But on the numerator, we put pressure or the concentration of the product. And this is how you can relate to that. So if the K is greater than 1, that means at equilibrium, you have more products because that K is really products over the reaction, products over the reactants, either pressure or the concentration. And we will say products are favored. If the K equals to 1, your our results are really neither products or reactants are favored. Delta G standard at this point equals to 0, and the reaction kind of has stuck in the middle when it has this almost the same amount of the reactants and the products at that K equals to 1. But if the K is less than 1, that means when equilibrium established, your denominator, which is the concentration of the reactants, are greater, and the reactants are favored at the equilibrium. So this is how you can interpret this. So let's take a look at this example problem 18.9. They're giving us the reaction, um, calculate the equilibrium constant Kp for this following reaction at 25 degrees Celsius. H2O liquid, decomposing into hydrogen gas and oxygen gas. But they said use the data from the appendix 2 to calculate that. So of course we need to find the free energy, standard free energy. And to find the standard free energy, what we will do, we will use the appendix, we will get the standard free energy of formation of the hydrogen gas, of the oxygen gas, and H2O liquid. We will put this into that equation. Of course, we have to multiply the standard free energies by the coefficient because they're only per 1 mole, but I have 2 moles over here and 2 moles of H2O. So when we put all the numbers from the appendix 2, we will get that the standard free energy for the following reaction is 474.4 kilojoules per mole. So then we will use this formula because we want to find the Kp here. So this is delta G standard. This is R, this is T, and we will find the logarithm of Kp equals to minus 191.5. Then to find the Kp, we have to take the antilog of that, and we're getting that the Kp here really equals 7 times 10 to the minus 84. So this is a very, very small number. Kp is a very, very small number. So if the Kp is a very small number, much, much less than 1, of course. So what we say over here, that the reaction reaches equilibrium, the reaction will favor the reactant, meaning not that much of the reactant. When the equilibrium will be established, we will have a lot of reactant, H2O liquid, not that much of the product, hydrogen gas and oxygen gas. So, and that doesn't happen. H2O, the water, liquid water, does not decompose into hydrogen gas and to oxygen gas to any great extent. So, and you can do the same for the other problems like that. You can calculate any problems using that equation. Um, I just want to talk here about the thermodynamics in living systems. So what this really telling us about is a coupled reaction. The coupled reaction means that sometimes the reaction, let's say, a zinc sulfide decomposing into the zinc and sulfur is not favorable. As you can see, it's a positive delta G. So it cannot happen spontaneously. But when it's coupled with another reaction, which is actually spontaneous and delta G is minus a negative. So when they both of them run together, so the second reaction will enable the first one to happen also. So yes, as you see, we can couple the one reaction which is not spontaneous with another one which is spontaneous, but they kind of share the same intermediate substance. So then the second reaction can drive the first reaction and they both will happen spontaneously. So that's the coupled reaction. So in the coupled reaction, or the actually in a living system, they play a very crucial role. So that will be it for the chapter 18.